This video is about cyclic groups, and we start with the definition of what a cyclic group is. A group G is called cyclic if there is an element A in G, so if there is one A in G, such that G equals to the set of A to the power of n, where n is an integer. Such an element A is called a generator of G. So the usual notation is if the group is cyclic, it's generated by an element A. So this will be the generator. A generates the group G. A very first example, I can call it example number 1, is the set of the integers. The integers are generated both by 1 and -1. Any positive integers, for instance, is generated by 1. 1 plus 1 plus 1 plus 1, etc. A second example is Z8. Z8 is generated either by 1 or by 3 or by 5 or even by 7. Well, let us check this. For 1 is too easy, right? 1 plus 1, 2 plus 1. So let's just see what Z8 is. So 0, 1, 2, 3, 4, 5, 6 and 7, right? Okay, let's see if it is true that the element 3 is a generator of Z8. So 3 will be the set of 3. So now 3 plus 3 equals 6, right? 6 plus 3 equals 1, right? We are adding module 8, right? 1 plus 3 equals 4. 4 plus 3 equals 7, and 7 plus 3 equals 5. Sorry, 7 plus 3 module 8 equals 2, right? Right. Okay, so equals 2, and 2 plus 3 module 8 equals 5. Equals 5. Okay, and 5 plus 3 equal 0, module 8, right? 0. So Z8 is 0, 1, 2, 3, 4, 5, 6, 7, and the element 3 generates the set 0, 1, 2, 3, 4, 5, 6 and 7. So we can say that 3 equals Z8. 3 generates Z8, the entire Z8. Okay, you can check that for 5 too, and for 7. Okay, not hard to do. So so Z8 is a cyclic group, right? Remember the definition of cyclic group. A group G is called cyclic if there is an element A in G such that G generates, A generates G, A generates G, right? That's the case here. 3 generates Z8. You can also check that not all elements are generators. For instance, 2. What is the set that 2 generates? 2 generates the set with element 0, 2, 4, and 6, right? So this is not Z8, right? So the set generated by 2 is not Z8. So 2 is not a generator of Z8. What about U8? Is that a cyclic group? Is U8 a cyclic group? The roots of unity. Well, this will be the set of 1, 3, 5, and 7, right? Let us see. What does 1 generate? Well, 1 generates the set 1. And what about 3? 3 generates the set 3 and 1. What about 5? 5 generates the set 5 and 1. And 7? 7 generates the set 7 and 1. Okay? So U8 is different from any set generated by for all A in U8, right? So there is no element in U8 that generates U8. Okay, so U8 is not cyclic. This theorem is very important. This is a criterion for a to the power of I to be equal to a to the power of j. Let G be a group and A belong to G. If A has infinite order, then all distinct powers of A are distinct group elements. So all A's, a to the power of 1, 2, 3, 4, they will all be different if A has infinite order. If A has finite order, say n, order n, a finite order, then the set generated by A will be the identity A squared till A to the power of the order n minus 1, and A to the power of I will equal to the power of j. So this will happen if and only if n divides I minus j. If A has finite order, then there will be a finite set of powers of A, and there will be a moment where a certain power of A will equal another one. And this happens if and only if n divides I minus j, I minus j. And we are going to prove this now. The very first sentence or proposition of the theorem is really easy to prove. Let G be a group and A belong to G. If A has infinite order, then all distinct powers of A are distinct group elements. This is really easy, because if A has infinite order, there is a non-zero n such that a to the power of n is the identity. If a has infinite order, okay, if a is 1, 2, 3, 4 and it is infinite, there is a non-zero n such that an is the identity. So a to the power of I at a point will be equal, I will be equal to j. This, if this happens, so a to the power of I minus j will equal the identity. For this to happen, we have to have I minus j equal, a should be to the power of 0 in order to be equal to the identity. So I minus j should be equal 0. And the first proposition is proved. I made a huge mistake here, right? If a has infinite order, there is no non-zero n. This number doesn't exist, such that a to the power of n is the identity, right? Because a is of infinite order. So we take a to the power of 1, 2, 3, 4, and we will never reach the identity. Okay? Because if a to the power of I equals a to the power of j, that means that a to the power of I minus j equals the identity. So I minus j would have to be 0, but that will never happen. Okay, so the first proposition is proved. Okay, if a has infinite order, there is no non-zero n. Okay, now we are going to prove the second proposition. So the second proposition is, if a has finite order, say order n, then the set generated by a will be this one, will finishing at one point, and of course then there will be a I that will equal j. A to the power of I will be equal to the power of j. That will happen if and only if the order of n divides I minus j. So let us say that the order of a equals n. So if this happens, we prove that the set generated by a will be the identity a till a minus 1, right? We will prove this, okay? We assume that the order of a is n, and we will prove that then the set generated by a is this one. Okay. Well, the elements a, e, a to the power of n minus 1, they will all be different, okay, that's for sure. Okay, why is that? Because if a to the power of I equals a to the power of j, well, but j is greater than 0 and is smaller than I here, and it will be smaller than, what is the biggest one here, this one, n minus 1. Okay, So if a to the power of I equals a to the power of j, this implies that a to the power of I minus j equals the identity. But this is a contradiction, because n is the least positive integer such that a to the power of n is the identity, right? So all elements are distinct. What I said here, okay? All these elements are distinct. Okay, we just assume that the order of A is n, okay, and we have to prove that all these elements are distinct. Okay, so they are distinct, because if any of those elements, any two of those elements are equal under these limitations, right, j and I has to be positive, both, I greater than j, and they all have to be less than n minus 1, okay, because that's the biggest one. Okay, so if a to the power of I equals a to the power of j, then a to the power of I minus j has to be the identity. But this will contradict the fact that a to the power of n is the least positive integer that equals the identity. Okay? A to the power of I minus j cannot be the identity, because this is a contradiction to the fact that a to the power of n is the identity. Okay? After a to the power of n minus 1, you would get a to the power of n. But you don't get this. Why? Because that's the identity. Right? Okay? Now, suppose that a to the power of k is an arbitrary member of the set generated by A. By the division algorithm, there will be an integer, two integers k and r, such that k, q and r, such that k will equal qn plus r under this usual limitation. Okay, so this is the limitation from the division algorithm. Okay, then a to the power of k will equal a to the power of qn plus r equal a to the power of qn times a to the power of r, right? And a to the power of n to the power of q times a to the power of r equals the identity, because this is the identity, right? A to the power of n, do not forget a to the power of n is the identity. So the identity to the power of q will be equal to the identity, and the identity times a to the power of r equals a to the power of r. So that a to the power of k will be an element of the set generated by A. And this proves that the set generated by A is this one. Okay. Next, we assume that a to the power of I equals a to the power of j, and prove that n divides I minus j. We begin by observing that a to the power of I equals a to the power of j implies a to the power of I minus j equals the identity. We use this trick at the beginning of the proof. Again, by the division algorithm, and you use this division algorithm in the second part of the proof. There are integers q and r such that I minus j equals qn plus r under these limitations. Then a to the power of I minus j equals a to the power of qn plus r, and therefore the identity will equal this and will equal a to the power of r. But since n, the n we choose, is the least positive integer such that an is the identity, we go back to this was the one we chose, we must have r equals 0. Okay, this r here has to be 0, so that n divides I minus j. Okay, conversely, if n divides I minus j, then a to the power of I minus j equals a to the power of nq, and that's the identity nq. That's the identity to the power of q, but that's the identity. So a to the power of I equal a to the power of j, and that concludes the theorem. Okay, so that was the proof. Okay, that was this proof here of this criterion. Let G be a group and A belong to G. If A has infinite order, then all distinct powers of A are distinct group elements. Okay, we proved this one. Okay, I'm sorry for this huge mistake here. The no, don't forget this. And the proof is if A has infinite order, there is no non-zero n, of course. Okay, if A has finite order, say order n, all that n that was in the proof was this n, we took an arbitrary n, okay, then the set generated by A will be this one. The set will be this one, and A will to the power of I will be equal to a to the power of j if and only if n divides I minus j.